So I'm going to be talking about this work titled Randomness, Efficient Noise Stability, and Generalized Epsilon Bias Sets. And this is joint work with Donna Moshkowitz and David Zuckerman. So the overarching theme of this talk is about approximating random distributions. And one can say that the study of pseudo-randomness is about approximating random distributions using a small random seed. And in computer science, the most common distribution that people study to approximate is the uniform distribution on n-bit strings. And this is due to applications in de-randomization and other things. And the famous idea is that de-randomization is about finding hay in a haystack. So what this means is that there oftentimes in computer science applications, you have your space of 0, 1 to the n, n-bit strings, and there's an overwhelmingly large fraction of these strings that are good, meaning that, say, your algorithm outputs the correct answer on an overwhelmingly large fraction of the random strings that it can take as input. And the point is that this means that if you have some random variable z with a small support that's, say, well scattered in some sense among this space of 0, 1 to the n, then this random variable will also hit this set of good strings very often, and therefore you can use the randomized algorithm or what have you with a very efficient seed length, with a very efficient use of randomness. So as we said, the seed length is often an important feature here, as this can determine how efficient or wasteful an algorithm is in terms of runtime, or just in terms of the amount of randomness that you need to use to run the algorithm. And in many cases, a seed length of 1 times log n is ideal. And what this means is that the size of the support is linear in n. And this is the regime that we're going to be studying in this talk. We're going to be studying how can we get a 1 times log n support for a very specific type of distribution. So let's look at a little bit more formally what we really mean by approximating a random distribution. Let's say we have some family of functions f, and we have some function g, which stands for generator, which takes input s bits of random seed and outputs n bits. And let's say we have some distribution d that we want to approximate. What we say is that the distribution that you get when you feed in a uniformly random seed to g, we say that that distribution approximates d to within the epsilon with respect to our family of functions f, if for every f in our family of functions, the probability that this f outputs 1 on an input generated from our generator is epsilon close to the probability that it will equal 1 when it's fed from this target distribution d. And we often say that this means that g fools f with respect to d. And as we said before, oftentimes this distribution d, the target, is the uniform distribution on 0, 1 to the n. But it's not too hard to imagine. Computer scientists use more than just the uniform distribution in their applications. So in this talk, we're going to be looking at how to fool a simple class of tests with respect to a simple non-uniform distribution. And more specifically, we're going to be looking at fooling the class of linear tests with respect to the product distribution with marginals p. So let's define what all this means. So the definition of a product distribution with marginals p, which we denote d sub p comma n for some p between 0 and 1, is a distribution on 0, 1 to the n, where every bit xi of the distribution is picked independently from all the others, and the probability that it outputs 1, or heads, is equal to p. And we'll just say d sub p if the length of the string n is clear from context, but this distribution is a fairly simple generalization of, say, the uniform distribution, where now the probability of getting heads is no longer 1/2, but now some small, we can think of a small probability p. And The class of linear tests on 0, 1 to the n is just the set of all functions on n bits that outputs 1 bit. That is of the form f of x, where the input x is just the inner product of x with alpha for some fixed alpha in 0, 1 to the n. And this is just the plus and times of this inner product is just done over f2. And you might notice that when you take p equals 1/2, this is just the same thing as epsilon bias sets, if you know what those are. So this is the main theorem of our work. It states that if you have p a power of 2, say something like 1/4 or 1/8 or 1/16 or what have you, then there exists a distribution z on 0, 1 to the n that epsilon fools linear tests with respect to d sub p comma n. And more importantly, what we can show is that this z only requires something like 1 times log n plus some lower order terms, number of bits of uniform randomness or seed to sample from. So what this means is that we have a nearly linear size, so something like n log n or n poly log n size support for z. So before we go about proving this theorem, let's look at some applications in computer science for approximating d sub p comma n. And the main application that we were thinking of when we were doing this was approximating the eigenvalues of the noisy Boolean hypercube. And the noisy Boolean hypercube, it's a well-studied object in computer science, specifically in Boolean function analysis and also in hardness of approximation and PCPs. And what the noisy Boolean hypercube is it's a graph with the vertex set 0, 1 to the n, such that a random step in the graph, starting from some node A, which is a string in 0, 1 to the n, is equivalent to picking some random r from the distribution d sub p comma n and moving to a plus r. So what you can think of this as is a random step is equivalent to taking your current node or your current 0, 1 string and independently and uniformly, independently flipping each bit with probability p. And visually, you can think of this as, you have your Boolean hypercube, and for every, at every single node, there is some non-zero probability of moving to every other node in the hypercube, except it's less likely for small p to move to more farther away nodes, because this would require you to flip many bits, which happens independently with small probability. But what you can notice is that the number of edges in this graph that have non-zero probability is very dense. In fact, it's essentially a complete graph if you think of it that way. So what we can show is that if you take any distribution z on 0, 1 to the n that approximates d sub p to within epsilon with respect to linear tests, then you can consider this new graph with transition matrix as follows, that will denote t sub p sparse. This is also a graph on 0, 1 to the n, and now a random step in this graph is just picking a random sample from z instead of d sub p comma n and moving to the node a plus r. And again, this a plus r is this bitwise addition of the vectors. And you can show that in this case, t sub p and t sub p sparse have the same eigenvectors, and the corresponding eigenvalues of each eigenvector are epsilon close to each other. And the key point is that now the number of edges in t sparse that have non-zero probability is only linear in n. And this means that you need only a very small amount of randomness to carry out this random step. And the eigenvalues, or the spectrum of this graph, is close to the original spectrum of the noisy Boolean hypercube. So just as a taste, You might ask, why do we care about eigenvalues of the noisy hypercube? Well, they're closely related to this important notion called stability from Boolean function analysis, for one thing. For example, if you take a function from -1, 1 to the n to the interval 0, 1, you can say that the stability of f is just defined as the inner product of f with t sub p comma f. And here what we mean is that you take f and you think of the vector f as a truth table of length 2 to the n, and you just multiply this by the transition matrix for the graph t sub p, which we just defined. And then we take the inner product of that with f. And you can similarly just define the sparse stability of f as the inner product of f with t sub the transition matrix of t sub p sparse multiplied by f. And you can show that in this case, it's actually true that the stability is epsilon close to the sparse stability for every f. And this notion of stability, this original notion of stability, has some important applications in the analysis of certain types of PCPs related to hardness of approximation. And what we are showing here is that these tests that these PCPs and these PCP results use can be approximated using an efficient, a very small amount of randomness. So now that we have some taste of why it might be interesting to study approximating this d sub p comma n distribution, let's look at the construction for how to approximate this with a very small seed. So as a building block, we're going to use epsilon bias sets, which is a little bit, which is natural, since as we showed before, when p is 1/2, this task of approximating d p n is just the same as using epsilon bias sets. So let's remind ourselves what an epsilon bias set is. It's a small set S, which is a subset of 0, 1 to the n, such that for every alpha in 0, 1 to the n, we have that if you draw a random element from this set S, and you look at the inner product of alpha with that element, the probability that that inner product is 1 is epsilon close to the probability that the inner product is 1 when you draw x from the uniform distribution over all possible strings in 0, 1 to the n. And a second building block that we'll use is the k-wise epsilon bias set. And this is basically the same as an epsilon bias set, except the alphas that we consider only have to be ones where the Hamming weight, or the number of ones in alpha, is at most k. And some theorems about these two building blocks. We know that there are explicit constructions of epsilon bias sets that require 1 times log n random bits to specify a random bit in S. So the seed length is only something like 1 times log n. And for k-wise epsilon bias sets, where we only have to worry about alphas where the Hamming weight is k or less, we know that we can do this with log k plus log n random bits, so much cheaper for small k than the original epsilon bias sets. So now that we have these building blocks, let's look at a first approach for constructing our desired distribution Z. The first attempt is just very natural. Let's consider the bitwise AND of log base 2 1/p independent epsilon bias sets. So visually, this is what we're doing. You have log 1/p n-bit strings, and each one independently is generated from some epsilon bias set, say from the one that we looked at before, which only requires a 1 times log n seed length. And we just take the bitwise AND of these. So if this first column is all ones, then the output is 1. And for the rest, if any of the columns contains a 0, then the output will be 0. And we just do this. And it's not hard to see that the marginals should be close to p. And intuitively, if you just took completely uniformly random, not epsilon biased, but like just log 1 over p independent uniformly random samples from 0, 1 to the n, then this would give you exactly d sub p comma n. So it's not too crazy to think that if you take log 1 over p independent samples from an epsilon bias set, that you can get as output when you take the bitwise and something that approximates d sub p comma n. And this turns out to be true, but the seed length is something like log base 2 1 over p times log n. And that's just because we're taking log 1 over p samples. And each sample takes 1 times log n seed. And this is too costly for what we're aiming for, because we want a 1 times log n seed length, which seems to be ideal. So the way to fix this construction and to improve the seed length is this key observation that if you look at some alpha in 0, 1 to the n with Hamming weight k, the probability that the inner product with x, when x is taken from d sub p comma n, is 1/2 minus this term 1/2, 1 minus 2p to the k. And what this means is that for very large k, or alphas with very large Hamming weight, this term is very close to 1/2. More specifically, if you take k, at least this O of 1 over p log 1 over epsilon, the probability that you get 1 is actually something like epsilon close to 1/2. And in other words, it's epsilon close to what it should be in the uniform case of 1/2 comma n. So what we're showing here is that the behavior of these parities on the subset where the alpha is 1, when you're drawing from d sub p comma n, is actually very close to just the behavior of the parities of the uniform distribution. So for very large k. So what this means is that we really only need to worry about the fine-grained behavior of p versus 1, the d sub p versus d sub 1/2, or the uniform distribution, for very small indices, very small Hamming weight alphas. So here's our new construction. Again, we're setting this k to be something like 1 over p log 1 over epsilon. And now we're altering the construction so that we're generating a single string from an epsilon bias set, and then independently the rest of the strings are generated from a k-wise epsilon bias set. And you can see here that the seed length is something like 1 times log n plus some lower order terms, because the k-wise the k-wise epsilon bias sets are very cheap seed length wise and don't really contribute anything to this log n term. And if we use an efficient epsilon bias set, we can get a 1 times log n seed length in total. And so why does this work? Well, the intuition, as we saw before, is the same. If we look at the first case, where we're looking at an alpha where the Hamming weight is small, so we're looking at, say, a very small subset of indices of this, we can use the same intuition as before and show that since all of these strings are generated from a k-wise epsilon bias set, and this subset is of size k or less, we're going to faithfully approximate the distribution of the distribution d sub p comma n, where the marginals have probability p. Now, in the case where alpha is greater than or equal to k, we can also show that this works, because now we need to just show that the output of the parities is close to 1/2, or just what it would be in the uniform distribution. And this turns out to be true, because if you look at just the rows generated from the k-wise epsilon bias sets, or in other words, just these, all the rows except the first row here, you can show that there's a very high probability that some row is going to have all ones in it. And what this means is that the overall parity that you get when you take the bitwise AND of this, and then take the parity of that with the bitwise AND of all this, and so on and so forth, really only depends on whatever bit is here, right? Because no matter what the parity of this guy and this third guy and this fourth guy altogether is, since this one is all ones, the probability that this final thing is 1 or 0 or whatever is just completely dependent on whether this bit is 0 or 1. And because this is generated from an epsilon bias set, we know that's very close to 1/2. So we know that the entire output, or the entire parity, is close to 1/2, which is what we want in this case. So that concludes the sketch of the construction, and I'll give some closing remarks now. So in summary, what we did is we constructed a random variable on 0, 1 to the n that approximates this specific non-uniform distribution, d sub p comma n, with respect to linear tests. And the support size is nearly linear in n. And this construction involves just using these out-of-the-box standard epsilon bias sets. And we should note that this approach only works for p a power of 2. It'd be interesting to see how to do it for other p's. And one thing I'd like to mention is that this approach might be considered wasteful in terms of entropy. As you noticed, the key idea is just that we simulate a coin that has bias p, or has probability p of outputting heads, by using log 1/p independent fair coins. And this is wasteful in terms of entropy. This idea in general is just wasteful in terms of entropy, because we're using log 1/p bits of entropy to simulate some random variable that has less than 1 bit of entropy. So a natural question, I think, is that can you obtain a better result, or a more elegant result, if you assume that the bits of the seed also have bias p? So in this case, you can simulate a coin with bias p using only one coin of bias p, which is more efficient than, say, having to use multiple coins of full entropy in order to simulate a coin with less than 1 bit of entropy. And I guess an overarching question of this work is, are there more applications to approximating non-uniform distributions using a small seed? It'd be nice to see if there are interesting applications of our specific scenario where we're just trying to approximate this simple product distribution with respect to linear tests. Thank you.